Here we will derive a formula to find exponential growth or decay equation relating to percentage. That is, if an initial quantity, that is initial quantity A0, has a continual percentage growth or decay by R% over certain period, then the final quantity A after n number of such period can be represented by this equation. Let us discuss it and understand it. Okay, so the initial quantity is A0. So this is the initial quantity, and R%, let us first consider growth. R% growth over a period. So initial quantity is A0 after one period. Now this period, certain period, can be 1 hour, 1 year, 1 decade, 1 century, 1 month, many things. So after one period, the growth will be R%. So the initial quantity, after one period, the quantity will be, initial quantity is A0 plus growth, for plus, that is growth will increase, R% of this quantity. So that means R% of A0. If we calculate it, we will get A0 plus R% means R division 100 and of A0. So now if we take this A0 common, we will get 1 plus R division 100. So after one period, that is after 1 R% growth, the quantity will be A0 times 1 plus R division 100 for growth. But if we consider decay, that is decrease, then this plus will become minus. This plus will become minus. This plus will become minus. So this will be the quantity after one period. So after one period, this is the quantity. Then after two period, after two such periods, this is the initial, that is during second period, this is the initial quantity, and R% will increase or decrease based on this. So let's consider this is 1. So after two periods, it will be A1 plus for growth minus for decay, R% of this A1. After one period, quantity is A1. After two periods, so in this second period, another R% growth or decay will happen based on this A1. So it will be, similarly, if we calculate this, it will be A1, 1 plus or minus, plus for growth, minus for decay, R division 100. Now A1 is this. So if we replace this A1 with this value, we will get A0, 1 plus minus R division 100, and this 1 plus minus R division 100. So this same thing multiplies twice, so we can write it in square form as A0, 1 plus minus R division 100 square. So after two period, it is square. In similar way, if we calculate, then after three period, A3 will be A0, 1 plus minus R division 100 to the power 3. So in general, that is what the equation is, that after n period, the final quantity will be, so after n period, if we go like this, after n periods, final quantity, if we denote by an, it will be A0, 1 plus minus R division 100 to the power n. So this power n will be the power. So this is the exponential growth or decay equation. This plus is for growth and this minus is for decay. Form exponential equation for following situations. Here we are given two problems, A and B. So let us first consider A. We need to form exponential equation for the situation where population increases 7.5% per year. So now the exponential relation that we know is, if we have an initial quantity of A0 and growth or decay by r% in a period, and there are n number of such period, then the final quantity an after n of such period can be written as a0 1 plus minus r division 100 to the power n, where plus is for growth and minus is for decay. So here population is increasing, so the problem is a growth problem. Now if we consider p0 is the initial population, and growth per year r equals 7.5% per year, and which is a growth, then pt, if we define pt as the population after t years, then using this formula we can write the final quantity, that is the population after t years, pt equals initial population, that is p0, 1 plus, because it is increasing so it is growth, so it will be plus r is 7.5 division 100 to the power t. So this is the exponential relation or equation that represent this scenario, where p0 is the initial population and pt is the population after t years. So now if we calculate it, 0.75 division 100 will be 0.075 and plus 1, so it will be p0 1.075 to the power t. So this is the pt equals, this is the exponential equation that represent this scenario. Let us do question B. A radioactive material has a half-life of 1 year. So a radioactive material reduced to half in every 1 year. Half-life means the mass of the radioactive material reduces to half within a year. So in a year time. So if we consider m0 is the initial mass of the radioactive material. Here in 1 year, time period is 1 year, and it reduced to half. So it is reducing, so it's a decay problem. And how much it is reducing? It is reducing to half. So the decay rate is 50%, because half means 50%. Decay rate is 50%, so and it is a decay. Then mt, if we define mt is the mass after t years, then using this relation we can write the mass of the radioactive material after t years equals initial mass bracket 1 minus, now this is decay relation, so it is minus, the mass is reducing, so we will consider minus 1 minus r, the decay rate is 50%, so it will be 50 division 100. And how many such period? N period. Here it is t years, so t periods, so it will be t. So we will get, if we simplify it, we will get m0, this is half, 0.5, so 1 minus 0.5 is 0.5 to the power t. So mt equals this. So this is the exponential relation that represent this radioactive material situation, where m0 is the initial mass and mt is the mass after t years of decaying.